Okay, in this problem, Biff is wearing his super slippery shorts down a slide. How fast is he going at the bottom? Okay, thank you, Biff, for wearing your super slippery shorts, because that means, since he's wearing his super slippery shorts, then we're going to say, no, that the friction is essentially zero, or friction is negligible. We'll talk about friction at some point, but not yet. And there's no spring in this one, but we all know what's going to happen is he's going to either a gust of wind, or he's going to just lean forward a little bit, and he's going to start to accelerate, and not so much there, and more here, and not so much there. And he's going to end up going at some speed when he gets to the bottom. Is this a problem we can use Newton's second law for? No, because there's so much we don't know. We don't know these angles, we don't know these lengths, etc. So this is a pure energy analysis problem. So let's get into this. We start with what should be in our system that will allow us to answer this problem with the least amount of hassle possible. Okay. Generally, if you have something moving in your system, you want to include that thing that's moving. So in this case, we're going to include Biff. Now, this is going to get a little weird here, but there's something else we need to include in our system. You say, well, I don't see a spring, etc. Right. Here's how it works. Do you notice that Biff is going downhill? Why is he... Yes, you do. Okay, so why is he speeding up? Because there's gravity. Okay. Biff is in a gravity field. And here's the basic rule. I just want you to apply it. If you come across any problem in which there is change, something in your system is changing height, then I want you to include gravitational potential energy in your analysis. If you want to push me on that after the AP exam, okay, I'll tell you, no, you didn't really have to do that, but that's the way you want to go. Because here's the deal is, we don't want to think of gravity as doing work. And if you don't include gravitational potential energy, then you have to think about, well, how much work does the Earth do? And I don't want to do there. So I want to take, and it gets a little weirder here, so I want to include gravity. I want to include, there you go. I want to think of Biff as his gravitational potential energy is changing. Well, it turns out that when you decide what's in your system, you need to include all energy storage mechanisms. Okay, you can't see that. I got to change the angle of this camera. All right, you need to include in your system everything that is storing the energy. Now, I think Biff is going to have kinetic energy, so we need to include Biff. In the previous problem, we had compressed springs. So if you wanted to include elastic potential energy in your problem, you would want to include the spring. Well, here, what is the energy storage mechanism for gravitational potential energy? And it's not Biff. It turns out it's the Earth's gravity field is what really ends up storing gravitational potential energy. And where does this gravity field come from? What big, round, physical thing what creates this gravity field? And it is the Earth. So this is going to look like, what the heck? But this is how it works. Okay, so if you have a problem that involves changing height, the easiest thing to do is to not think about gravity doing work in, and then, because if it's going downhill, gravity's doing work, positive work. If it's going uphill, gravity's doing negative. Just forget that. Just say, I want to include gravitational potential energy, and the one thing you need to do is you just need to add the Earth in your system. And so what we're going to start calling this is going to be the Biff Earth system. I know it sounds crazy, Because you say, Biff and the entire Earth? Yes, we need the entire Earth because we need its gravity. In this local area, you can't have gravity just in, all I needed is on this little slide. Well, you can't just say, I only want a little bit of the Earth's gravity field, or I only want a little section of the Earth. No, it takes all of the Earth to create the gravity field at this. So just get used to that, okay? Because then this becomes a pretty easy problem. Oh, by the way, Biff is embarrassed about his mass. So we don't know the mass. He's gained a little weight. Certainly happens to me. And he just doesn't want to tell us what her mass is. Okay, so just keep that in mind. We don't know. You don't know my mass, dude. Okay, fine. Maybe we can't solve the problem. I think we still can, but all right, just keep that in mind. We don't know the mass. But we can write out the statement of energy. Okay. So now that we've got the Earth, the entire Earth in this system, what are there any external forces acting on Biff and the entire Earth? Well, I can think of a normal force acting. So at every point, as Biff goes down this slide, there's going to be these little, normal. Okay, so yes, in terms of like, is there any work being done? Well, are there any external forces? Because you need to have external forces in order to do work. Okay. Sure, there's external forces. There's a normal force pushing on them up the whole time. But is that normal force doing any work? Do you see? Okay, at all times, what's the orientation of the normal force to any motion that's going on? Whoops. And the answer is they are completely perpendicular. So the normal force does no work. And there's no other external forces, okay? There's no friction. The normal force, sure, it's an external force acting on Biff, but it doesn't do any work because none of the force is in the direction of the motion. So there's no work, okay? There's no work in or out, so work equals 0. So that means our statement of conservation of energy says, look, whatever energy was in our Biff Earth system at A is still present at B. It's going to be in a different form, but the amount of energy is going to be the same. Okay, so what is the form of energy at the top? He's not moving, by the way. Okay, so V sub A. V at A equals 0. All right. But of course, he's elevated. He's elevated in a gravity field that's provided by Earth. Okay, so Biff and the Earth, I might make that mistake too. I just would say Biff has gravitational potential energy. No, it's the Biff Earth system has gravitational potential energy. And that's going to equal in magnitude to the kinetic energy that it is going to be just in Biff, okay? But the kinetic energy in our system at B. Okay. Now, let's remember how we quantify these two forms of energy. Gravitational potential energy is quantified by mgh at A. Oh, I guess I need to come up with some number here. Let's say, I forgot, sorry, this is 10 meters. Okay, forgot to add that. That is known. Okay, and then the kinetic energy is going to be 1/2 mv at B squared. Okay, so what I'm doing then is, and I recommend you do this for all of your problems, is when something is changing height in your system, figure out in your problem what's the lowest point it can go, and we're going to say that's essentially our height is 0 line. It's kind of like the origin of a frame of reference. You can put it anywhere you want, but I think putting it at the lowest point makes it easiest, okay? So we're going to say that the Biff Earth system has no gravitational potential energy when he gets to the bottom, and he has some at the top. Okay, now let's go back to this idea of Biff, a little sensitive about his mass, isn't going to tell us what his mass is, okay? Can we still determine the speed of Biff at the bottom of the ramp. And hopefully you're raising your hand going, ooh, 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 because that is correct. You can answer it because mass goes into gravitational potential energy and mass goes into kinetic energy. And so we have an M on both sides. And so, yes, we can completely answer this question. We can't say how much energy Biff has. So you don't get everything when you don't know the mass. You can't know how much energy he has at the top in the system, at the top in gravitational potential energy. You can't know how much is in kinetic energy. But you can tell me, I can tell you how fast it's going. Have you seen that before? Free fall, different masses. They're going to be going to the same. Okay, all right. We've seen that before. So once again, we have this kind of, since basically gravitational mass, which is on this side, and inertial mass on this side are the same, we get into another one of those kind of like free fall type things. All right, let me just get back on track here. So if I rearrange this, I can bring this guy over here. And basically what you're going to get is the speed at v at b squared equals, this, not this, that's too early, 2gh. So if I want to get rid of that guy, I need to do the square. So bottom line is, I can easily get the speed of Biff at the bottom of the slide by taking the square root of 2 times the strength of the gravity field times the change in height. Notice I could care less whether this was a straight slide, whether it went up like that and down. It truly is path independent so long as this condition is true. Okay, so let's see if we can do this without a calculator. No? Well, we can get close. All right, so 2 is 2. G, I'm just going to use 10 newtons per kilogram, 10 meters per second square. The change in height is 10 meters. So I've got the square root of 200, and whatever that is, okay, is it going to be, I don't want to embarrass myself, okay? So I'm just going to let you, I know it's more than 10, and I know it's less than 20, but I don't know, I'm going to guess 12, 13, 14, something like that. Okay, there it is. Another problem. Key point is when things are changing height, you're going to want to include gravitational potential energy. You do not want to get into this idea that gravity is an external force. Negative work, positive work, don't go there. Just use gravitational potential energy, but that means you've got to include the Earth as part of your system. Bye.